Hello everyone, I am Pinal Rana, a third year PhD student at IIT Bombay. My paper title for the WCMNM conference is An Experimental Study on Laser Ablation of Ultra-Thin Silicon Nitride Layer for PERC Solar Cell. PERC is stand for Passivated Emitter and a Rear Contact. Let us first understand the structure of PERC solar cell and need for laser ablation. So, the PERC solar cell is a modified conventional solar cell with a higher efficiency, which consists of 4 different layers. At the front side, anti-reflective coating is there to absorb maximum solar radiation. In the middle, silicon substrate is there to provide free electrons and hole pair. At the rear side, aluminum back surface fill is used to reduce bulk recombination losses. Further, to reduce surface-to-surface recombination losses and to create more free electrons by reflecting light, one extra layer is added at the rear side, which is known as a passivation layer. In our case, silicon nitride is used as a passivation layer. The thickness of a passivation layer is 80 to 100 nanometer and it's behave as an insulation medium. Therefore, in order to create electrical contact, a small opening is created in this passivation layer. There are various methods through which this small opening can be created. First one is photolithography, second is chemical etching, third is diamond stretching, and fourth is laser ablation, out of which laser ablation is a fast, effective, and efficient method. However, there are various challenges involved with the laser ablation process. The removal of 80 to 100 nanometer thin silicon nitride layer without subsurface damage is very difficult. Further, at a higher temperature, nitrogen is diffused into the liquid silicon, which make nitrides and it behave as an insulation medium. So, my main aim is to optimize the range of process parameter for the ablation of a silicon nitride layer with minimum subsurface ablation and a negligible nitrogen content. In order to achieve this, first we have conducted experiment at a different fluence value, followed by the characterization. Ablation depth and width is measured using optical microscopy and scanning electron microscope. Further, nitrogen content is evaluated using energy dispersive X-ray analysis. In the end, the data is analyzed to obtain the optimal parameter. The experimental setup is shown in the figure, in which, using reflecting mirror, laser is directed towards the workpiece and focus using focusing lens. The SLTL scribo machine with 532 nanometer wavelength is used for the experimentation. During experiments, the power is varying from 0.06 volt to 0.52 volt by controlling value of current. Further, frequency is ranging from 40 to 50 kHz. During experimentation, pulse width and spot diameter is kept constant, which is 25 nanosecond and 25 micrometer respectively. On the bottom left corner, the sample specification is mentioned. P-type polysilicon with 80 to 85 nanometer thick silicon nitride coated sample is used with the resistivity of 3 to 5 ohm centimeter. The measured refractive index of a sample is 2.01. On the bottom right corner, image of a laser scan sample is shown. The black line indicates the line scan at a different laser parameter. Here, result obtained from the scanning electron microscope is presented at 2.4 joule per centimeter square fluence value. If we observe carefully, at the edges of the ablated region, pores are formed, whereas the central part is relatively clean. During laser heating of a silicon nitride layer, silicon nitride is decomposed into the silicon and the N2 gases. No clear path available for the N2 gases to escape from the edges, which results in formation of a pores. These pores act as a recombination center in PERC solar cell and reduce its performance. However, the size of pores is around 10 nanometer, which can be easily removed during subsequent processes. The laser ablation profile obtained from the optical microscopy is shown on the right-hand side figure. The profile is shown at two different values of fluence, namely 1.5 joule per centimeter square and 2.4 joule per centimeter square. At 1.5 joule per centimeter square, bulge is formed, whereas at 2.4 joule per centimeter square, crater is formed. When the value of fluence reaches to the threshold value, breakdown and blow-off happen through various mechanisms. Further, at the edges, hump is observed, which could be due to the melt expulsion. After analyzing SEM images and optical data, following is the proposed mechanism of laser ablation. Since the thin silicon nitride layer is transparent to the laser radiation, it does not absorb any radiation. Laser absorption occurs only in the silicon substrate. Subsequently, the silicon nitride layer also gets heated up due to the conduction of heat from the underlying silicon. Therefore, the temperature is maximum at the interface and gradually decreases outward in the silicon nitride layer, with the top surface having the lowest temperature. At lower fluence, it is likely that the temperature of the top surface of silicon nitride layer does not reach to the normal boiling point for ablation to initiate. However, the subsurface region could be at much higher temperature, leading to the bulging of a material. And with an increase in fluence, breakdown and blow-off happen, which leads to the formation of a crater. The variation in ablation depth and width with the fluence is shown in the present slide. The measurements were taken at 3 different locations and average value is reported. From the figures, it can be observed that no ablation occurs below 1.5 joule per centimeter square laser fluence value. Both ablation depth and width increases with an increase in fluence. This is because the heat input per unit area increases with an increase in fluence value. The increase in ablation width and depth with an increase in laser fluence is very significant, initially up to 3.9 joule per centimeter square. Beyond this value of fluence, the increase in ablation depth and width is marginal. This could be due to the effect of plasma shielding, which becomes significant at a higher fluence, leading to saturation of ablation depth and width. Nitrogen content in the ablated region plays a vital role in solar cell performance. If silicon nitride layer is not adequately removed, the printed aluminum back surface field may not make a proper electrical contact with the beneath silicon owing to its insulation property. This may lead to higher recombination losses. Therefore, EDX data is presented here to evaluate nitrogen content. In the figure, we have shown the variation in the nitrogen content across the ablated and non-ablated region. If we observe carefully, in the ablated region, nitrogen count is lower compared to non-ablated region. During ablation, when the temperature reaches to the 2150 Kelvin, silicon nitride is decomposed into the silicon and nitrogen. Ideally, nitrogen in the ablated region should be zero. However, traces of nitrogen is presented due to the chemical reaction with ambient air as silicon reaches at a higher temperature. Further, on right-hand side figure, the variation in the ratio of nitrogen count in an ablated region to the non-ablated region is shown with the fluence value. This ratio could be used to define the quality of ablation. If the ratio is close to zero, it is considered as an efficient ablation. In the figure, it can be observed that with an increase in fluence, the ratio is steep decline initially and so marginal increase after that. This data suggests that the moderate moderate value of laser fluence is preferred for an efficient ablation. Here are some of the important conclusions drawn from the present study. First one is bulging of silicon nitride layer occur at a lower laser fluence due to the thermal effects. Crater is formed at a higher fluence as a result of breakdown and blow-off. Initially, with the rise in fluence, the ablation width and depth increase significantly, whereas the increase becomes marginal at a higher fluence. Nitrogen content reduced in the ablated region due to the thermal decomposition of a silicon nitride layer. From the present study, the optimal value of a laser fluence is 2.4 joule per centimeter square. I would like to thank SLTL Private Limited and NCPRE Group for their continuous support during experimentation and characterization. Thank you.